Hello everyone, in this video we will be covering section 5.2, Euler's method. So Euler's method will be the first numerical method that we use to solve initial value problems of this type. Euler's method is a very simplistic method like you will see right now, but the simplicity of its derivation, which we're going to do right now, can be used to illustrate techniques involved in the construction of some more advanced methods, which we will get to in the coming sections. So the idea, Euler's method is pretty easy. Remember that we're trying to solve a problem of this type, where dy dt is nothing more than the slope, okay? And let's say that this is the graph of the differential equation. So the idea is pretty simple. First, you're gonna cut the time interval into n equal pieces, okay? So you go from A to B. So h is gonna be the step size. It's gonna be b minus a divided by n, where n will be the number of steps you want. Therefore, the value for ti, to find these two values, you can see you're just adding h every time. So therefore, ti will be equals to a, which is the starting point, plus I h, where I is going to be equals to 0, 1, 2, all the way to n. And this is exactly what we have right here, okay, this part. This one. Okay. All right. So we have used Taylor series in this class maybe 20 times. So we're going to use it 21 times now. If you apply a Taylor series expansion here, we will end up with this formula. Here we're expanding around Ti. So you can verify that this is nothing more than the Taylor expansion, which we have used multiple times. Remember here, Ti is less than Ci, and this is less than Ti plus 1 for the second derivative. Also remember, this is what we consider the error. Okay. So if you do some basic algebra, you can see that you can rewrite this as y of Ti plus 1 is equals to y of Ti plus h, y prime of Ti plus h squared over 2 y double prime of Ci. You should check this by yourself, and it's very easy to see that clearly h is equals to Ti plus 1 minus Ti if you use the definition of Ti. All right, so therefore from here, which again, this is nothing more than Taylor series or Taylor expansion, from here we get Euler's method, which will be this. So we're going to assume that Wi is approximately equals to Yi. So Wi is going to be the approximations to Yi. For I is equals to 1 all the way to n. And therefore the method will be the following. W0 will be equals to alpha. Remember, this is the initial condition. And then Wi plus 1, which will be this part, is going to be equals to Wi plus h f of Ti Wi for I equals to 0, 1, 2, all the way to n minus 1. So in essence, the next value is just the previous value plus h, which is the distance on the time, times the function evaluated at this time. At that point, you already know this, and you will know this. So this is very, very easy. So this is pretty much just like finding the slope, you think about it. And as you can see from this graph, if you only do one step, well, this graph is not very close to the real thing. But if you cut the time space into smaller pieces and you do this multiple times, you can see how it's getting closer and closer to the real thing. Okay. Now Euler's method is just this part, which you can see is very, very simplistic. So you always start with the initial condition, then to get the first value, you look to the previous one, plus the function evaluated at the two values that you already know, times h, which is the time interval. Let's do one example. Okay. Let's say that we have this differential equation where the value for a here is 0, the value for b is 2, and the initial condition is this. The value for n has to be given. Let's say that n is equals to 4. So if that's the case, then h, or the time step, will be 2 minus 0 over 4, which is equals to 0.5. And since we have 4 steps, we're going to start in 0. So this will be t0. So you're going to have t1, t2, t3, and then t4. Therefore, this will be 0, this will be 0.5, 1, 1.5, and 2. All right, so the algorithm tells us to do the following. So W0 is always given because that's the initial condition. So W0 in our case is just alpha, which in this case is just 0.5. That's it. Then W1 is going to be now W0 plus H f of T0 W0, which in our case, this will be equals to 0.5 plus 0.5 because H is also 0.5. And this will be the function evaluated at T0 is 0 and W0 is 0.5. So therefore this will be 0.5 minus 0 squared plus 1. And when you simplify all of this is 1.25. Like I say, this method is pretty simple. If we continue the same way, then now W2 is going to be equals to W1 plus 0.5. Now it will be W1 minus 0.5 squared plus 1. And once you simplify all the values, and you should check this, once you plug everything and simplify, you should end up with 2.25. All right, so then if you keep doing the same thing, W3 will be W2 plus 0.5 times W2 minus 1 squared plus 1, and this is around 3.75. And finally, W4 will be W3 plus 0.5 times W3 minus 1.5 squared plus 1, which is around 4.4375. So therefore, this implies that y of 2 is around W4, which is equals to 4.4375. Right, let's look to the same problem that we just have, which was y prime was equals to y minus t squared plus 1, and t was between 0 and 2, and the initial condition was 0.5. Instead of having n equals to 4, let's say that n is equals to 10. So therefore h now will be 2 minus 0 divided by 10, which will be 0.2, which you can see the step being 0.2 here every time. Now this will be the values, which again they're not hard to find, but it will take a while you do it by hand. This is the exact value, and this is the absolute error. So you can see that as the value for h gets smaller, the error is getting also smaller for the most part, except for the last one. The next thing we had to figure out is, well, now that we saw that the method was pretty easy, how can we get some error bounds for this method? So we're going to start with lemma 5.7, and the lemma says this: suppose that x is more than -1 and you have a positive value m, then we have the following. We're going to need this in the following proofs. So how do we prove that this is true? Recall from calculus 2 that e to the x is equals to the sum from I equals to 0 to infinity of x to the I power divided by a factorial. In fact, this was the Maclaurin series that you learn in calculus 2. Okay, so this is a Taylor series. Now, if we want to have a Taylor polynomial, we can say from here that e to the x is equals to 1 plus x plus 1 over x squared times e to some c, because we're going to stop in here. Okay, remember this keeps going forever, so you stop at some point. That's where we put the c. Well, using that result, then we have the following: 0 is clearly less than equals to 1 plus x if x is more than -1. Okay? But this is less than or equals to 1 plus x plus 1 over x, 1/2 x squared e to the c. And clearly, this is less than equals to e to the x. Why? Because e to the x is the whole thing going all the way to infinity, and this one we stop only after 2 terms. Well, therefore, this implies that 0 is less than equals to 1 plus x, and this is clearly less than or equals to e to the x. So therefore, that means that 0 is less than equals to 1 plus x to the m power, and this is less than or equals to e to the x to the m. And that's it. So that's the proof for that part. Now let's look to the following lemma. It says that if s and t are positive real numbers, and then you have a sequence that satisfies a of 0 is bigger or equals to minus t over s, and then this recurrent sequence is also true for each value of I equals to 0 all the way to k minus 1, then that implies that e to the I plus 1 is less than or equals to e to the I plus 1s times this quantity minus this quantity. Okay, so how do we prove that? So here is the proof. All right, so we know that ai plus 1 is less than equals to 1 plus s ai plus t from here. Okay, but this is also equals to less than or equals to 1 plus s times 1 plus s times ai minus 1 plus t plus t. Well, how do we get that? Well, this gives you all of this, and this t is just this stay right here. All right, notice that this one should be 1 plus s. It's not written correctly, so it should be 1 plus s ai minus 1 plus t. Now, if you distribute this, we'll end up with this is equals to 1 plus s squared times ai minus 1 plus t times 1 plus s. Okay? Where the last part, you just factor the t out, you end up with 1, and then the t is multiplying this part, so that's how we get this. If we do this one more time, we end up with the following. This should be less than or equals to 1 plus s, that will be q, ai minus 2 plus t times 1 plus s plus 1 plus s squared. All right, you may want to stop the video for a little bit and check that this is actually the case. If we keep doing this, this will be less than or equals to 1 plus s to the I plus 1 a0 plus t times 1 plus s plus 1 plus s squared plus all the way to 1 plus s to the j, where you should notice that this part is a finite geometric series, okay, where the value for r is 1 plus s. Okay, let's continue the proof on the next page. This is what we have so far, that a of a plus 1 is less than or equals to 1 plus s to the I plus 1 power times a0 plus t times 1 plus s plus 1 plus s squared, and so forth, all the way to 1 plus s to the I power. Well, remember we say that this was a geometric series. This is pretty much the key to what we're going to do next. And if you remember from pretty much not elementary school, but from elementary algebra, there is a formula to add a geometric series. And if you add all of them, the formula tells you to do this. It should be 1 minus 1 plus s to the I plus 1 divided by 1 minus 1 plus s, and you will end up with 1 over s, 1 plus s to the I plus 1 minus 1. So this is the sum formula for a geometric series. You can find the formula in any college algebra book. So therefore, from here, we will end up with I plus 1 should be less than or equals to 1 plus s to the I plus 1 a0 plus t over s. You combine this with this one, and then this is equals to 1 plus s to the I plus 1 minus 1, which is equals to 1 plus s to the I plus 1 times a0 plus t over s. If you combine these two, minus t over s. And finally, by lemma 5.7, which is the one we proved before this one, we get that ai plus 1 is less than or equals to e to the I plus 1 to the s power times a0 plus t over s minus t over s. You should check this. This is the case. All we did was to use the lemma from the previous page. Okay, and that's the end of the story for this one. All right, now let's look to theorem 3.9. This is what it says. Suppose that f is continuous and satisfies the Lipschitz condition with constant L on a convex set, and that there is a constant m such that the second derivative is bounded by that value for all values of t between a and b, where yt denotes the unique solution to the initial value problem. Then we let W0, W1 to Wn be the approximations generated by Euler's method, like we did in the previous example, for some positive value integer n. So then this will be the error bound. The distance of the Euler approximation and the exact value will be less than or equals to hm. Remember that m is the bound of the second derivative, h is the time step, L is the Lipschitz constant, and this will give you the error bound for Euler's method. The proof for this term is a very good candidate for the test, for a test question. So when it comes to the proof, this is obvious when I is equals to 0. Why? Because, well, at y equals to 0, the initial conditions for both of them are the same. Like I say, this is a pretty good question that could be on the test. This term uses lemma 5.8, which is the one we just did right now. And obviously, you need to know to apply the Lipschitz condition too. So the Lipschitz condition. So you should try this proof by yourself. Now, there is a big weakness with this error bound, and the main weakness is that this one requires that you know the second derivative of the solution. So if you already knew the solution, why will you try to approximate it? However, note that technically, if these two exist, which most of the time they do, the f dt and the phi dy, so if both exist, then y double prime by definition is equals to the derivative with respect to t of y prime, which in our case is the derivative with respect to t of f of t yt, which is equals to d of f dt by the chain rule, okay, plus d of f dy of tyt times f of t yt. All of this is by the chain rule. So therefore, it is possible to obtain an error bound for y double prime, even if you don't know yt explicitly. But it's not always the case. However, the most significant thing about theorem 5.9 is this, that the error bound depends on h linearly, which means that if you decrease the value for h, you will get more accuracy, or your result will be more accurate. However, this is not taking into account round off error, which means that if you decrease this, it's going to require more computations, and the more computations, the more round of error that can be introduced in the method. So we'll discuss that on the next part. Take a look at table 5.2 here, which is comparing the actual error with the error bound that was computed in the previous example. Notice how the error bound is bigger or significantly bigger than the actual error, especially as the value for t increases, even though the error bound was calculated using the actual derivative, because we know what yt is, so therefore we have the exact solution, and hence we can find the second derivative and bound it. So even though we have this, you can see that the error bound is significantly bigger than the actual error. And the reason why is because technically we were not using W0 and Wi like we thought we were using. This one didn't take into account the round of error. So if we introduce the round of error, that's why we end up with something like this. So let's look to the next theorem, which is going to explain what's going on here. Theorem 5.10 says the following. Let y of t denote the unique solution to the initial value problem. I'm just going to call it right now double star. And let u0, u1, all the way to un be the approximations obtained using a star, where a star will be this. U0 will be alpha, the initial condition, plus some error. And then ui plus 1 will be ui plus h f of t I w I plus delta I plus 1, where the delta will be the error, the round of error introduced. Okay, so we're going to call this star. Here, delta I is equals to the round of error associated with ui. So this is the method we're using instead of this one. Okay, this was the method we used before. So let me just make sure that this is clear. Okay, so the solutions we did before when we applied Euler's method was this. Okay, here we're just talking about specifically about the error bounds. So this is the method we use, but when we calculate the error bounds, it actually doesn't take into account the round of error, which this one does. So this is for theoretical purposes. So instead, consider this one, and this is for round of error. Again, let me make sure that this is clear. If I ask you to use Euler's method, this is the one we're going to use. If we're trying to find the theoretical error bounds, this is the method that we're actually using. Okay, so let me go back to the theorem. So theorem 5.10 says this again. Let yt denote the unique solution to this initial value problem, and u0 to un be the approximation obtained using star, which is this part. And if delta I, remember delta I is the round of error associated with ui, is bounded by some constant for each I from 0 to n, and the hypothesis of theorem 5.9 also holds, then the actual bound will be this, which is not linear anymore. If you remember when we did section 4.1, 4.2, this was very similar to the the error bound for the methods of approximating derivatives, where if you decrease this one, well, this one increases. If you decrease this one increases, and so forth. I don't expect you to do the proof for this one. The thing that you need to be aware is this part. So if we look at this piece only, you should notice the limit as h goes to 0 of hm over 2 plus delta over h is equals to infinity. So therefore there must be a optimal value for h if we just rely for this part for the error. And we did something similar to this. If you use calculus, you can check that the value for h is this. So this will be the minimum value you should use for h. If you use any values of h less than this one, then this will increase the round of error. Therefore, this should be the lowest that h, the value for h should be. All right, that's it for section 5.2. And this is the last part that will be on the first test. Sorry, the second test.